So in this video, we're going to talk about arcs and chords in a circle. So the first thing we should talk about, some of these theorems talk about circles being congruent. Yes, it is possible for circles to be congruent. In order for one circle to be congruent to the other, they both have to have radii that are congruent. So two circles are congruent when their radii are congruent, because that means, so look at this circle. If their radii are both 5 units, that means no matter which way I draw it, from the center, any point on the circles will be 5 units away from the center. So in order for circles to be congruent, their radii have to be congruent. Okay, so something else you might learn, in this theorem it talks about congruent arcs have congruent chords. What that means is it all connects to the central angles. So if you remember, we spoke about a central angle in a circle. So let's look at this central angle. Let's say this is circle A, and angle CAT is 80 degrees. Okay, well we know then that arc CT is also 80 degrees. If I were to construct another angle within this circle that was also 80 degrees, or another angle that's 80 degrees, let's call this B and D. Well, we see that arc BD would also have to be 80 degrees because in a circle, if the central arc is going to be the same measure, central angle, is going to be equal to its arc. Here, this angle is 80, so its arc is 80. So if the central angles are congruent between two congruent angles, then that means that the corresponding arcs are congruent. So if angle CAT and angle BAD are congruent, that means that arc CT and arc BD are congruent. And the same works the other way around. If I were told the measure of the arcs, that means that the angles would also be congruent. Similarly, if I were to, let's just make these look like vertical angles, okay? So if I were to say that these two arcs are congruent, then the two angles would be congruent. Okay, so that's what we just spoke about. Another thing that would be true is if I were to draw a chord, remember a chord is a segment that connects 2 points on the circle. If we look at this circle, well, we see that we have radii. Remember, all radii are congruent. And you might notice that these two triangles I created are congruent. If the two triangles are created, then that means, let me just call this chord AB, and let's call this chord CD. You notice that when the central angles were congruent, that meant that the corresponding chords were congruent. So if the central angles are congruent, that means that the chords are congruent. And if the chords were congruent, that meant that the central angles are congruent. All of these are linked. Literally, you can make actually one long statement. If central angles are congruent, that means that the arcs would be congruent. If the arcs are congruent, that means that the corresponding chords are congruent. And it works the other way around. If chords are congruent, that means the arcs are congruent. It means that the central angles are congruent. So if you were to put this in your record book, you could actually just write all of this one statement. Okay, it represents actually 6 different relationships. So let me show you a practice problem. So in this picture, I told you that circle A is congruent to circle B, which means that all of the radii between the two circles are congruent. So look at that, SAS, both of those triangles are congruent. So say you didn't even know the theorem, because you know SAS, you'd know that triangle ACE would have to be congruent to triangle BDF. I knew again that these radii were congruent because if circles are congruent, then the definition of congruent circles is that their radii are congruent. So anyway, say you either knew because of congruent triangles, CPCTC, or the theorem that we just reviewed, if the central angles are congruent, that means that the corresponding chords are congruent. And which chord? It's the chord that is formed by the intersected arc. So to solve this one, I'll do 2x plus 10 equals 30, and I'll solve that. And I get 2x equals 20, x equals 10. Okay, let's do another one. So another theorem that we have is that a diameter or a radius, if a diameter or radius is perpendicular to a chord, then it bisects that chord. Okay, so what that looks like, if I have a circle, it's called a circle A, and if I have a chord, remember chord is a segment that just connects two points on the circle, so I'll call that B and C. If I know that A is perpendicular to that chord, what then happens is that the two segments that are created would be congruent. You notice this also says that it bisects the arc. Well, let's say if I extended down this line. Yes, the arc can be bisected. So from B to, I'm just going to name this F. BF would be congruent to FC. Okay, so if the diameter is perpendicular to a chord, then it bisects. Okay, it bisects that chord and the arc. This is helpful in problems like this. So let's say that this is circle A, and in circle A, I'm just going to name these. You are given that AC is perpendicular to BD. I'm also going to give you that angle B equals 30 degrees, and that the radius of the circle is 5, let's say it's 50 root 3. Okay, so here's the problem. In circle A, AC is perpendicular to BD, angle B is 30 degrees, the radius in the circle is 50 root 3. I want you to find AC. Okay, so well, to do this problem, first let's mark what we know. If AC is perpendicular to BD, that means we have two right angles. We know that AC, so if you look at the picture, AC, that segment, it's not a diameter nor is it a radius, right? It's like this just little piece that's hanging out there. But look, it actually is part of, if I were to extend it, it is part of the radius. Okay, so even though it's not a fully drawn radius, it does have the same properties that the radius had in seeing this problem. You notice I didn't even draw this all the way down, but it was inferred that that segment was part of the radius. The way I know that is because it has an endpoint on the center. Okay, but I only want to find the length of AC. I just want to find this. Okay, so here's what I'll do. I'm just going to mark, I know this is 30 degrees. I also know that these are congruent. I know that the radius is 50 root 3. So AC is not the radius. Look at that. The radius has to actually touch the circle. So yes, from A all the way to the circle, that's 50 root 3, but that might not help me very much. But if I look, there are other radii in the picture. From A to B, that's a radius. So look, that's 50 root 3. Okay, so if you look, I have a 30, 60, 90 right triangle. So here the hypotenuse is 50 root 3. Half of that would be 25 root 3. So AC equals 25 root 3. Another question I could ask you is, say I said find BD. Well, to do that, remember 30, 60, 90, so here we have 30 degrees, that's x. The hypotenuse was our 2x, and this is our x root 3. So if our short leg is 25 root 3, to get the long leg, I'm going to have to multiply it by root 3. So it gives me 25 times root 9, which is a whole number, 3. So that's going to give me 75. So from B to C, that's 75. But I wanted to find the whole length, BD. Well, because we know that AC is perpendicular, it bisected, so BD is 150. Another theorem that we have is that congruent chords are equidistant from the center of a circle. When we say equidistant, or when we talk about distance, it infers perpendicularity. Okay? It infers perpendicularity, meaning if, say this is a wall, and if you're standing here, and I asked you what is the distance from where you are standing to that wall, you wouldn't measure it at an angle. You would measure it the perpendicular distance to that wall. So when we talk about distance, we are inferring a perpendicular segment. That is important for this concept because if I have a circle, so it says congruent chords are equidistant from the center of a circle. So let's just say that AB and CD are congruent. If they're congruent, it says they're equidistant from the center. So if this is the center of the circle, equidistant just means the distance from this chord to the center would be the same distance that this chord is from the center. So E to F to E to Z are the same distance. That's helpful because if you remember the other problems about the perpendicular segments, we also know that that segment would bisect the chords. So just to go over, when we talk about equidistance, if these two chords are congruent, that means that the segment that I draw to mark that distance would be congruent. So if AB is congruent to CD, that would then imply that EF is congruent to EZ.